welcome to day 3 of exponential functions. Today we are going to talk about writing models for real-life situations that can be modeled by exponential functions. But before we do that, we are going to review how to write percents as decimals. The reason why we need to know how to do this is because when you perform operations with percents, you cannot keep them in percent form. They need to be either in decimal form or in fraction form. Usually decimals are easy because there is a pattern, which we will discuss right now. Okay? So, looking at this, we have 25%. Okay, percent. How many cents are in a dollar? 100. So percent per 100. So if we have 25 per 100, that written as a decimal is 0.25. Okay, and same over here, 7%, we have 7 per 100, which that is 0.07. Okay, if you look at how our percent is related to our decimal, percent decimal, okay, we can basically take this value right here aside from the percent sign. So if we just mix the percent sign and say 25, what we do is we move the decimal point that's after 25 over 2 spots, and that gives us our percentage. Okay, so here if we would have just taken 7 has a decimal point right here, we bump it over 2 spots, fill in the empty space with a 0, and you get 0.07. Okay, so with 13%, we're going to take the number 13, move the decimal spot 1, 2 to the right, so 13% written as a decimal is 0.13. Okay, here we have 23.4%, so we're going to take 23.4, take this decimal, move it 2 spots to the right, and we end up with 0.234. Okay, and last but not least, we have 0.02%. So if we have, 0.2. So we take 0.2, move this guy to the right 2 spots. So here, 0.2% is actually 0.002 written as a decimal. Okay, just a quick refresher. We should know how to do that by now, but sometimes you forget. So here's some refreshing, and now on to exponential growth model. Okay, here we have an equation. Y equals A times the quantity 1 plus R to the T. Okay, this is our exponential growth model. Now if you notice here that this A is the same A that we have in that we've been speaking about for the last 2 days. Okay, except here in a real life situation, it is the initial amount. Okay, so in a word problem, you'll be given an initial amount. That is your A, which makes sense because that is where your X equals 0. And if you think in terms of a real life situation, usually you start at 0. So some logical connection there. Okay, R is our growth rate, and this growth rate needs to be written as a decimal. Okay, so in a problem you'll be given a percentage for a growth rate. You'll need to write that as a decimal and then add it to the 1. Okay, when you add it to the 1, that gives you your growth factor, which from our equations in the past 2 days would be our B. Okay, our growth factor. And if you're adding a decimal to 1, that's going to give you a number bigger than 1, which means if your B is bigger than 1, that we do in fact have a growth model. Okay? And then last but not least, our T is now in the exponent, which is the time period. Okay, it could be months, it could be years, but look at what the question is asking and answer according to that. Okay? So, using this model, we are going to answer this question. The owner of a 1953 Hudson Hornet convertible sold the car at an auction. The owner bought it in 1984 when its value was $11,000. The value of the car increased at a rate of 6.9% per year. Part A, we need to write the function to model this. Okay, so we're going to use this format. Okay, so looking back through the problem, let's color coordinate this. Okay, our initial amount, the owner bought it in 1984 when its value was $11,000. That is our initial amount. That is our A. Okay? So far we are going to have Y equals 11,000. Okay. We're going to have 1 plus. We need to find our rate. The only rate in the problem, which didn't have the word rate there until I wrote it in. The value of the car increased at a rate of 6.9%. So if we have 6.9%, we need to use a percentage in a decimal form. So we're going to take that 6.9, bump this over 2 spots, and that gives us 0.069. So we're going to add 0.069 to this. It's going to be a very colorful equation. And then our t at this point is unknown. So this is still going to act like our x from our equation the last 2 days, except it just has the letter t instead of x. Because this function depends on the time. It depends on how long the car has been owned, how old it's been. So this is our it's our independent factor, or variable. Okay? So, we're going to add this. We will have y equals 11,000 times 1 plus 0.69 is 1.069 to the t. And that is our function. Okay? Alright. Part B says, how much is the car worth this year? What is the year? You guessed it, 2012. Okay, so that means we're going to be using this guy, but we have to figure out what our t is. So we're going to have y equals 11,000 times 1.069. Now, how many years are there between 1984, which is when he purchased it, and 2012? Any guesses? Okay, that's going to be 28 years. Woo! Okay, 28 years to this year. So that means that we are going to put 28 right here. Okay? Now we evaluate this. So we're going to have y equals 11,000. Order of operations, we need to take the exponent first. So we're going to have 1.069 to the 28th power, which is approximately 6.477. Okay, which means that our car is going to be about 6.477 times 11,000, 71,247. Okay? So you just find t and then plug and chug. End of story. Okay? Alright. Moving on to decay. Notice here we have the exact same model except for this. So when we're decaying, we subtract. When we are growing, we add. Okay, everything else means the same thing. The rate in the problem that we're decreasing by will be the decay rate. Our decay factor is 1 minus that. A is still our initial amount, and t is still our time period. Okay, so the only difference from growth to decay is plus to minus. Alright, so same thing here. We're going to write a function, and then we're going to do some calculating. The number of acres of ponderosa pine forest decreased in western United States from 1963 to 2002 by 0.5% annually. In 1963, there were 41 million acres. A, we want to write the function to model this. Okay. So, here we have y equals our initial amount, which is in 1963. There were 41 million acres. Okay, so we're going to, instead of writing 41 million, we'll just use 41, and then our answer will be given in millions. So we're going to have 41 times 1 minus. Okay, here we have 0.5, so we're going to take 0.5 and move this decimal over 2 times. So our decay rate is 0.005. And then we have this to the t. Okay, so our function is y equals 41 times 0.995 to the t. Okay, and notice that our b here is less than 1, which means we are decaying, so we are in good territory here. Okay, so looking at this problem, we need to figure out what our t is and then go from there. Okay, so our t is the amount of time that has passed when we are actually evaluating this. Okay, and this we're not evaluating in 2012, we're actually evaluating in 2002. Okay, so from 63 to 2002, we have 73, 83, 93, 39 years. So that goes into our t. Alright, so we're going to take 0.995 to the 39th power, which is going to give us 41 times 0.823. About that, I rounded a little bit. And then if we multiply that by our 41, we get y, oops, not what I wanted to write there. We get y is about 33.7 million acres. Not like my last name, but the number, million. Okay? That is modeling. Okay, so keep in mind, this is still the same format, a, b to the x, except we just have realistic things now. We have an initial amount, we have our decay factor, or our growth, if there's a plus sign there, and then our x is our time period. Alright, and we're done.